Hello. Today we are going to present the third partial project in which we will talk about the importance of calculus in real life. And our team is composed by Leonardo and Sofia. First of all, calculus is a branch of mathematics concerned with the calculation of instantaneous rates of change, which is known as differential calculus, and the summation of infinitely many small factors due to determine some whole, which is integral calculus, according to Berggren 2025. Calculus has several real-life applications in different fields. For instance, examples of applications of calculus in scientific fields are space exploration, telecommunication systems, computer science, engineering, medicine, pharmacology, business, meteorology, and music, according to Goldem Fanning 2025. And finally, calculus is very important in most branches of physics and engineering and in other areas of our daily lives because most natural events are able to represent themselves as small changes of a quantity that can be measured using calculus tools, as it involves the study of rates of change according to Russell in 2024.
Well, now we're gonna see a practical example that uh, involves the displacement, velocity, and acceleration as derivatives and integrals of each other in physics. Well, here we have an example in which there's a particle in free fall. As we can see from the acceleration function, we have that A is negative 9.81, or the gravitational force. So from that, by just integrating the acceleration formula, we're going to get that the acceleration formula is, if we integrate it with respect to t, we're going to have the velocity formula plus a certain c, and that c is going to be the initial velocity. So for example, if we have a problem that says that an object or a particle is being shot straight up at 10 meters per second, and the gravitational pull is dragging it down, when how would these three functions look like? Well, firstly, we know that the acceleration is just the gravitational force, so we know that that's a constant, as shown with the red graph. Then we know that the slope of the velocity graph will have a negative 9.81, because that's what happens when you integrate a constant. You just get that constant times the the variable of the function, right? So it would be 9.81 t plus c, and in that case, c would be 10, as it is the starting velocity of the function of v. Then we know that the displacement is going to be the integral of that v of t, right? So we'll use calculus to know that the integral of negative 9.81x plus c plus 10 is just going to be negative 1.81x squared over 2 plus 10x, or replace an x with t for it to make sense in a physics context, right? So we know that that will be the integral, and well, of course, we're gonna have a plus c, but that plus c in this case doesn't matter at all, because it just comes down to what our reference point is. So if we say that the initial point of the particle was 0, then the displacement initially would be 0, and that c from the integration constant would be 0 too, right? So that's why we see the green graph uh, going in the direction it's going. So basically, it just goes up and reaches a maximum, and that will be the point in which the maximum height is given, and that will be actually the point of the graph at that point, which is going to be like about 5. So we know that the maximum height that the ball or the particle gets to is about 5 meters. And then from there, it goes down and um, its height starts decreasing until it goes to 0 at about 2 seconds. And then from there, it goes lower than it was initially. Let's say it went up a cliff or something like that. We know how its height changes over time with that function. So from this practical example, we know how all of these functions are and relate to each other in a physics context. And well, here are references. We used a variety of sources, including GeoGebra, to get our graphs. So this is the end of the presentation, and thank you very much.